Hey folks, welcome to another episode of ASP.NET Core from Zero to Overkill. In this episode we'll take a look at async and await in ASP.NET Core. Not being a new topic, it's a topic that still causes a fair amount of confusion and errors and some people not understanding what's going on. They just follow the recipe, but I think it's kind of important to understand so it's easier to check the errors we got and try to fix them and make things work well. Even when we don't have errors, it might work better if we do things in a way or another. So yeah, I'll try to focus on this. So before we start coding, I wanted really to try to explain why we do use async and await and not just do what we did before we had this support. I think it's important to understand this. So just don't, like I said, so we are not just following some recipes. To try to explain this, I created a couple of diagrams. I think at first glance they might seem a bit overwhelming, and maybe they are, but I'll try to explain it the best I can. If you have questions afterwards, please do ask the questions and then I'll try to answer them. And even if in the future is needed, I'll make another video explaining some questions if it's necessary. But yeah, I think this is really important, even though a bit overwhelming at first. It's important to understand what we are doing instead of just adding async support and following the recipes. So even though this is a bit overwhelming at first look, it's simplified from what's really going on. I made this a bit more simple. Under the hood, a lot more is happening, but I think this is enough to understand the gist of it and not overwhelm even more with more complexity. I think this is kind of the right balance of complexity to understand this topic. So let's take a look at this. This first diagram that we're looking at, it's represents like a pre-async flow of requests. So let's start here. So we have these are for clients, then we have the server. So let's start small and then ramp up. So client 1 makes a request, R1, to the server. When the request gets to the server has a thread pool, which I represented as from T1 to T5. So this thread pool has 5 threads. It's not like this in real world, but let's pretend it is, just for explanation's sake. So the request reaches the server, and the server asks to the thread pool, give me a thread that's able to handle this request. And the thread pool, which has all the threads because it's the first request, gives back the thread 1. With thread 1, so the server passes the responsibility of handling request R1 to thread 1. So thread 1 goes here, does some business logic, some calculations, all that stuff. Let me use this tool here. So over here it's doing some business logic and all that stuff. And after doing the business logic, it makes a database access, as we see here. So normally a database access or service access takes longer to complete than just some calculations and stuff like that. So that's why the time is this long. So assuming this, what happens is we get the request R1, do the business logic, then make a database request, and the database might take a while to respond. During this time, thread 1 is blocked because it's waiting for the return of the database. So during this time, thread 1 is really doing nothing and only gets the response right here, which is a bit longer. During this time, imagine the client 2 makes a request 2 to the server then asks for a thread to the thread pool, has thread 1 is already working, then the thread pool passes the second thread. Of course, it will probably not be like this sequentially, but it's easier to explain. So then the server gets thread 2 to answer the request. So it passes R2 into thread 2. And like for thread 1, some business logic, some calculations, and access to the database for request 2. Again, might take a while, and during this time, T2 is blocked for response 2. So, in the meantime, we get the request of client 3, client 4, client 5 to handle all the requests. And because, like I said, we have a thread pool of 5, eventually we get to request 6. All the threads are occupied, so in client 6 makes the 6th request. We ask for a thread, but because we only have 5 threads, this time it's not as fast to provide the thread pool, because they are all occupied doing something. So in this case, request is blocked waiting for a thread to handle it. Meanwhile, if we go back here, the database finally responded here to the request 1. So thread 1 is unlocked and can continue. So maybe a little more business logic, some logging, whatever. And then when it's done, it returns request 1 to the server, so the server can respond request 1. And after returning the request 1, the thread 1 can go back to the thread pool. The sizes might not be the best, but I think it's understandable. So thread 1 goes back to the thread pool. So in the meantime, this thread can now be used to handle request 6, which was waiting for a thread. So with thread 1 back, we can now get the thread 1 and pass it along the handling of request 6. So we only can handle request 6 when one of the previous 5 is finished, because basically we can only handle as much requests as threads we have available, because they all get blocked. So in the meantime, request 2 finishes, the database response for request 2 finishes, request 2 can continue here on thread 2, and return, thread 2 gets back to the thread pool, so meanwhile could be a request 7 and all that stuff. So this is the problem we had in the past. One request, one thread. So, or we have lots of threads to get blocked, but that has an impact. We have lots of servers to handle that, which has a cost impact. So yeah, this was the problem we had in the past, and that it's one of the more important things that async and await try to solve. Not async and await is a simplified way to solve it. There would be other ways, like in JavaScript, callbacks that right now uses promises, which is kind of like the tasks and async and await in .NET. So, but it's easier to use async and await than promises directly. That's why we have now support for async and await in JS as well. So yeah, I think even though the diagram might be a bit complex, too complex, I think that's about it. Again, if you have questions, feel free to fire away. So this was pre-async times. Now let's take a look at async times. Using async and await, the graph, the diagram changes a little bit. So It's basically the same example. We have a client 1 that makes a request, gets to the server asks the thread pool, I need a thread to handle this. Thread pool gives it back thread 1. Thread 1 starts to process, makes the calculation, and makes a database access for the R1 request. But in this case, it doesn't block. It makes a request and goes back to the thread pool. So while we wait for the database to respond, thread 1 going back to the thread pool is now available to handle more requests. So if in the meantime we get request 2, and when the server requests a thread, if thread 1 is already there, it could get thread 1, it could get another. Like I said, this is just for example, but imagining that we have all the threads and it's all sequential. So we have 5 threads, so it gets back the first thread. So in this case, to handle request 2, we get back to thread 1, which some business logic and database access, during which the thread 1 goes back to the thread pool while we wait for the database access. Again, like I said, replace database access with web service, anything like that. So back to the thread pool, over here, back to the thread pool, we get request 3. Again, ask for a thread, thread 1 is already there, so get thread 1. Then, again, request 3 goes to thread 1. Calculations, business logic, database access for request 3, thread back to the thread pool. Okay. So let's go a bit here. Request back to the thread pool. Meanwhile, so right here we stopped having requests, but just for this example. In the meantime, the database response for the first request gets back. In this case, instead of, because thread 1 is no longer blocked waiting for it, it uses something really under the hood, and more complexity is there. So if I'm oversimplifying, and you know that I'm oversimplifying, sorry, but I think this is enough for people to understand what's going on. So in the meantime, when the database response gets back, it goes to something really low level, which are called IO completion ports, that signal when the IO is completed. So when we get back the database response, somewhere down there, it's requested a thread. In this case, we go back to the thread pool. All the threads are there because we did that, but maybe they weren't. We get a thread, and again we get thread 1. Never forget, this is an example. Other things are happening, but this is really simplified. So we ask for a thread to handle request 1. We got back again thread 1, but we could get thread 2 or thread 3, depending on what's available. It's not important, we get any thread. So with this, we forward the response that we received to the thread, so the thread can resume. So imagine the code like we will see in a bit. So when we do an await, it will do this, and when the request is complete, the response from the database is complete, it will get over here again to complete the code. So this part here is the line after the await line. So again, some business logic, whatever, return R1 to the server for it to respond back to the client. And this is wrong. Why is this here? It should be Ah, this is not very easy to use. Like so. So response cannot be before the return, of course. So we get back the response from the database, process it, what's after the await, return the response to the server. Thread 1 can go back to the thread pool, and after that, again, we get the response from R2 to the IO completion ports, which ask for a thread to the thread pool. Again, we get thread 1, we could get any other thing, and the response is again forwarded to the thread 1, does some business logic or whatever it has to do, and returns back the response and the thread to the thread pool. And again, the same. I'm being repetitive, so it's easier to understand. So get the response from the database for request 3, get the thread to handle it, we got back T1, forward the response to the thread to handle it, business logic stuff, logging, return R3, thread pool back to the T1 back to the thread pool. So really high level, that's how this works. So I think you could see what's the difference here. In this example, we were always using T1 because in the meantime, the database was processing what it has to do. So we did in one thread what in this one we needed for each client. And that's really how Node.js, for instance, works. With the event loop, and the server only has one thread to handle the requests, but we forward the requests to external services, databases, all that stuff. So one thread is enough. Of course, then we need to scale with more servers when it's needed, but it's the same logic. We need less threads to handle the requests because the time we are making I/O, we don't need to be blocked. We can just return the threads and they can do more work. So this is the gist of why we use async and await, to make our application more scalable. So we need less threads to do the same amount of work. Oof, I think that's it. Again, this is probably the most complex thing we talked about so far in this series. So if you have questions, don't hesitate to ask. So now that we understand why we go through these troubles to use async and await, let's use them. So let's get back here. So let's start. In this episode, we're not going with the database and web services yet, but we'll prepare for that. So we go to our business layer, where we have the contract, and we'll make this we'll prepare this for async and await. So a rule of thumb is everything that we want with async and await, we do task. So it returns a task. If it's a void method, it will just be task. If it's a method that returns something like these ones, it's a task of T. In this case, the task of the return we would do. There are some exceptions, like there is a sync void, but it's I don't think is useful in ASP.NET Core. I think it's maybe useful in WinForms, maybe Xamarin, stuff like that, but not in ASP.NET Core, so I won't talk about it. Something that is useful in ASP.NET Core, but it's a more advanced scenario, is a new type called value task, which is like task, but with less allocations, and it's useful for really high performance code. It's a much more advanced scenario. So I won't be talking about it right now. Right now we'll go with the classic task and task of t. So to make this all async, every method will return a task of the return they had. So task task. We do this because, as we know that all these methods go to the database, we want them to be asynchronous. We don't do all methods async, just the ones that go to the database, to an external service, stuff like that. If it's not an async method, no need to do it. It will only have impacts on performance. It's bad. So no, don't do it. Now, a convention, although some people disagree, but because Microsoft does it, I'll follow along, but some people don't like it, is to have the methods that are async, that return task, have a suffix async. So we do it as well. So async okay. Now we get some errors. Now the controllers are basically the same, but now we get this async. So over here, like we did in this one, now it will return a task of action result. And before we do this, you can go here. This is complaining because there is a await, but we need an async. When we do an await, we need the async. And we can have an async without an await, but it's useful for nothing, so we don't do it. Now it's the same in every place, so this will be a bit repetitive. Again, a wait. Now here again. A wait, and they sync here. Over here, no need, because it does nothing to need this. Over here, we again a wait, a sync task, and again a sync. Okay, so over here we are done. What is must be one of those allocation warnings. So this here is done. Of course, it's not really working because we must adapt the service implementation. But okay, so in the controller, all we do is this. We always await. I'll talk about some exceptions, not exceptions, in a bit, but okay, so this is, if we follow the recipe, it's really just this. Everything that does IO will be async. Every time we call something async, we do await. We do async all the way, so we don't block the threads. Now we go to implementation services, in-memory service. Okay. So this needs to be I'll take care of the errors in a bit. Let me just fix the method signatures. Okay, so now we're implementing the interface. Now we need to fix this. Like we saw in the controller, when we call something async, we do an await. But in this case, because this is not async, but implements an interface that expects stuff to be async, because when we go to the database, it will be async. In this case, we don't want to put here an async. It would solve the problem, but it would be worse because probably it would do some things that are not needed and unoptimized. So when we do an async, somewhere here we should have an await. So we don't have, so we don't need. But we need to return the task. When we want to return a task from a result we already have, that's called returning a completed task, we can do this task from result. So we already have the result, so we can return the task with it. We don't need to await anything. So what's the error? Cannot convert. Oh, because of stuff. We need to do this. Okay. So because we have a completed task, imagine if this was void, if we had something like public task stuff async. In this case, we could do return task completed task. So it's like a void, and we'll always return the same completed task. So we don't need to allocate every time a new task for the garbage collector to have problems in the future. But we don't have this problem right now, so task from result. Again, here it will be basically the same every time. Task from result. Task from result. So if we knew that this would never be async, we shouldn't do it. But because we know that in one of the following episodes, this will go to the database and be async, we just prepare the interface for that. So if we know, if we don't know, or if it's not likely it will be async, don't do it, because it's just more overhead. And that's it. It should be working as it was before. Let me go back here. I'll hide this for now. Or not. We need this. Okay, it's working exactly like before. Just prepared for async. So things to keep in mind: every time we call something async, we do a wait. It's important to do this. It's called the async all the way. We shouldn't block here the threads. I'll talk about that in a moment. But yeah, like this. In this case, because we are making like a dummy implementation, not async yet, we have things already done, so task from result is the way to go. Now let's make some interesting improvements to here. One interesting thing that we can do with this async stuff is making it cancelable. So let's do just that. We'll go back to the service and we'll add something that's called cancellation token. Task cancellation token. Call it CT. By convention, this CT or token or whatever is always the last argument of an async method. So always by the end. And then we go to our implementation. Well, so we'll add this here. Now, because this isn't really async, we have nothing to cancel yet. So let's make something here. Over here, instead of doing this, we'll do this. We'll put anything here, and we'll call a wait task delay, and give it some seconds. So we'll put 5 seconds. To simulate this takes 5 seconds to complete this operation. So now we're using a wait, so I put async, and I can pass it the cancellation token. Okay. Now every operation has a cancellation token, so it could be cancelled. If we go here, now to groups controller, now we have this error. And in ASP.NET Core, if we go here and put a cancellation token on the method, the framework will inject a cancellation token that's bound to the request. So we can now pass this. If we don't want to put it here, we could go to request.cancellation. HTTP context, cancellation. I don't know. There's a place where the cancellation token is, but I can't remember right now. Maybe it's in context? Okay, I can't remember. But there's a place where this cancellation token is. But normally I use it like this, so I can't remember where it is. So cancellation token. Cancellation token. Cancellation token. Okay. So it's working, hopefully, as usual. Okay. Refresh, create, and some group. We create, we do an edit, and it takes 5 seconds because we said it took 5 seconds, and it's done. Get back, edit, 5 seconds. It's that. Now let's get back, open developer tools. In network, okay, so again, edit, get, and 5 seconds later, it's done. Now let's try one thing. We'll make the request and click here. So it was cancelled and we got this warning. So that means that the cancellation token, when we did the request and it was cancelled, the ASP.NET received that information. So it cancelled it signaled the cancellation token that it should be cancelled. And in this case, task.delay just died. Let's just make an example here so it's easier to see. If we do this, nothing will happen. So the request will be cancelled. Let's see here. Starting. Okay, go here, create. Now when we edit, we click, the request was cancelled, but it wasn't cancelled on the server, so we thought it still needed to complete, although it didn't. So by ignoring the cancellation token, we cannot see this. If we use the cancellation token, we can see. If we were not using something that retrieves the cancellation token, or if we were doing some long-running calculations, we could do something like ct.throw if cancellation requested. So if we do this, basically it will, because the task delay is not looking at the CT, it will take those 5 seconds and then it will throw an exception because we asked it to stop. So some group, we click edit, it takes a while, we click, it will take a bit, but then the operation was cancelled. Okay, so this is how we can manually check for the cancellation request if we are not delegating to a database or a service or something like that. But most of the time we would prefer this. Okay, so this is it for this cancellation token. I think it's interesting that we can do this. So if we have some long-running operations, if the request was cancelled, why don't we just cancel everything instead of working for nothing? Now let's look at something that you really shouldn't do, but if you do, at least do in the not worst way. So, which is to do sync over async. Really shouldn't do it because there are problems. But let's take a look at it. So I'm just going to copy and comment this one, and we'll make another one, and we'll take the async out of it. So no wait. But this, let's take this here as well. But this returns a task. So we need to get the result because we can do this. So normally the first instinct of people is probably to go here and do dot result, which is the worst. Oh, I'm forgetting here. We don't have a cancellation token, but when we don't, we can use this cancellation token none. Ideally, we have the cancellation token, and when we don't, we pass in this. So, okay, so we do a result. In ASP.NET Core, besides blocking a thread that we shouldn't, there is probably no problem. But in other in other applications like ASP.NET Old School or WPF, WinForms, this could cause a deadlock. But I'll talk about that in a minute. Right now, let's just look at what's the problem with this. So we go here, and let's say that we go here and throw new not implemented exception. So let's go here, we'll add a logger, of groups controller, logger, let's do try catch exception. And let's do a log error exception, and we'll pass it expected. No, a better idea. I'll do this here. Not implemented exception. And it could, for instance, return content not implemented. So let's see what happens if we call this. Starting. Okay. Not implemented. Again, this is really not what I expected. Why is this doing this? I think they did some magic in ASP.NET Core, because this was not what I was expecting. Let me do this. Exception. And do let's try again. That's because .result is not supposed to give directly the exception, but another one. Kaboom. So the exception type is system not implemented exception. Oh, okay. I'm being stupid. Let me get this back here. That's because it's not really an async stuff. So let's do this. Async. I'll comment this. Do await, delay. So we want this method to really be async. And then throw a not implemented exception. So from what we are seeing here, we do .result, but there's an exception, so it will be here. Let's try again. It's running. Unhandled exception. Why? Is it not a not implemented exception? Clearly not. So let's try another thing. Catch exception. the other way around. And in this case, and return status code stuff. So we were expecting to get a not implemented exception because that's what we are doing here, but it didn't. It was an unhandled. So let's look at what's, so it's running and we got a 500, and let's look at the log. Error, unexpected system aggregate exception. Okay, this is the one I was expecting all along. So what happens when you do dot result? Basically, the exceptions that occur during the task, which may be more than one, are aggregated in an aggregate exception. So when it throws, when we do dot result, it doesn't throw what we expect, but throws an aggregate exception. So if we did, for instance, this, no need. Kaboom. And let's make it different so we can see. Go, 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 go. And then aggregate. Okay, so this isn't really what we want, because when we get one of these, we need to go aggregate, aggregate, and then inner exceptions, and then get the exception, all that stuff. Not good. So we want the exception, even when we are doing this that we shouldn't. So a way to do it is get a waiter, get result. So this is basically what the async state machine does under the hood. When the method is done, it calls get await or get result and gets the result. We shouldn't do this by hand, but in places where we need to do this, for instance, in the console application where the main method is not async, right now it has support, but in the past it didn't have support for async main methods. So this was what we did in those days. Now it has async main method, so no need for this, but let's pretend. So now the exception should go here. Let's try. Not implemented because it unwraps the exceptions, so we get the correct exception. Again, we shouldn't do this, but if we really need, go for it. But please don't. So like I said, this will block the thread, and like I will say in a minute, can cause a lot more pain. Now, even though this isn't a problem in ASP.NET Core, let me just make a little diagram again on why we shouldn't do this mainly in old school ASP.NET and in WPF and stuff like that. Remember basically what I've told you about. So we get a request. I'll put it like this time. So we get the request 1, and then we have thread 1 handling it. And now we make a database call. Imagine we make a database call. When the database call is complete, in ASP.NET Core there is no such problem, but in other types of application there was something called Synchronization Context that was each thread had. So when the request was done, it would try to go back here What happened? What? So thread 1 had a synchronization context, made a call to the database, which was an async call. Made an async call, but when this tries to get back, it needs the synchronization context. But the synchronization context is on thread 1, and thread 1 is blocked. Let's try to put this needs synchronization context. But because the synchronization context is with thread 1, the coming back, the completion part, like we talked in the over here, can't, or the thread that handles the database response can't have the sync context because it's here. The thread with the result needs the synchronization context, but the synchronization context is here. Because this is waiting for this, and this is waiting for this to be available, we have a deadlock and it won't go anywhere. I can show you this failing because we are using ASP.NET Core, but just recently we had this problem at work where we have some applications with old school ASP.NET where there was a synchronization context, and by doing this we made a deadlock. So for starters, we shouldn't do this, and that would solve the problem. If we do the async all the way, this would never have a deadlock. But one rule of thumb for these kinds of problems, when we are doing a library, because we don't know who will use it, if it's from ASP.NET Core, if it's from Xamarin, if it's whatever. One rule of thumb is on the awaitable methods, we can do this. Configure await false, by default it's true. That's why we don't need to do it. By doing configure to false, we're saying we don't need that synchronization context. So when we return, just go to any thread and do whatever you want. We don't need it, so we won't have deadlocks and stuff like that. This is really important. It shouldn't be, but because we don't know who and how we'll use our libraries, doing this makes our library less problematic for the others. So it's really no big deal to do it and solves problems. Most of the time we don't need the synchronization context. So, and in ASP.NET Core we really don't need. And in other applications like Xamarin, I think this makes some performance improvements, because by not needing the synchronization context, it's one less thing to worry about and copy from one side to the other and try to synchronize. By doing this, we are improving, even if a little bit, performance and avoiding those kinds of problems. But ideally, like I said, not here, ideally, we don't do this. We just, we do async all the way, and this way we have no problems of this kind. But I thought it was nice to show you these details. But okay, let's get back to this. So really be careful to avoid deadlocks, because these are the worst things to detect. If you're not expecting them, you'll be in for a pain in hours to understand why something is happening. But thankfully ASP.NET Core doesn't have this problem. The only problem we do with doing the dot result is thread starvation. So, but keep this in mind, because if you do libraries for other types of applications, it can be important. Let's look at some other interesting bits. This episode will be massive compared to the last ones, but it's a complex topic, so sorry. You can always pause and come back later. Sorry about this. Now, one thing that, if you already used this async stuff, you probably come across this question, which is, let's try something here. My mouse stopped. Yeah, it's back. Let's do something here interesting. Well, let's go here. I'll make a private method. Call async task group inner. I'll just copy this. And this one will stop doing this and will return inner get by id async id city stuff. Okay, so instead of doing async and await, we have an async method here, and we can just return the task, correct? Because it's a task, we can return it. So if you go back here, some group, edit, and it will work like before. 5 seconds, takes a long time, eventually it goes there. And we fix this, and we're happy. The filter is working. Okay, but now let's imagine here, after the delay, we throw an exception. New, not implemented because reasons. And we do this here. We know that that method might throw an exception, so we do try. Catch exception. and we return null. So if we do get by ID and we get an exception, we just return null. Let's look at new, create, same group, and we edit. It will take a while. And an exception. Why do we have an exception if we have a try catch? Well, because we did this return. Basically, by returning, we return the task outside. So if the try can't catch it because it's already returned. When outside does the await, it's when this will blow up. So if we want to catch the exception here, we need to do this. More than that, the exception stack trace will be different if we don't do this await. Sometimes that might be, we might want it if we don't have these problems like with the try. The problems, for instance, are a try catch, a using statement. If we return a task from a using, then in the inner method, the resources we are using might already be disposed when the task runs. So we shouldn't do return task from inside the using as well. Maybe other cases, but these are the ones I can remember. Okay, and besides that, like I was saying, the stack trace will be different. If we have always await, we can see the correct stack trace. If we bypass some, we might not. But if that's the only problem, sometimes it might be useful because it has a slight performance improvement, because without this async await, it's one less state machine. Every time I'm talking about the state machine without explaining, but basically the async await, the compiler translates this into a state machine. So inside of it, basically every await will be like a value in a switch, like 0, 1, 2, 3. Each line will be a value in the switch, and a callback will return to the method and say I want to go back to value 1 or value 2, and will proceed from the line after that one. That's how this async await works. So every time we do async await, a state machine is created. So if we can avoid it, it will have a performance improvement, but will be worse for the stack trace. So you need to consider this and see what's more important to you. In this case of a try catch and the using, you don't really have a choice. You need to do this, or you won't catch the exception. So now if we do this again, and we got nothing, because can even do this just to check. Same group, create, edit, 5 seconds, takes forever, and we got null. So this is important. Let me see in my sheets what we can do next. Oh, okay, this is interesting. Let's check the next thing, parallel requests. So let's go here. I'll get back to this to be normal-ish. Move this method. So imagine this application needed to do some external requests. Let's say private async task int, because why not? Async and whatever, cancellation token. And here we do an await task delay again with 1 second, and we return math.ren. Idiot. Let me put here private static read only random and we return dot next. And imagine over here, I'll just commit this for now, or not, let's 1 second here, and await, right? Call external Suffix Async, cancellation token, and we do another one. We won't be using this. Okay. So we are making this delay and then getting 2 results. Let's see how much time this takes. Then create some group. Okay. Now when we add it, it takes a bit, and we get the response in more or less 3 seconds, which is expected. So 1 second for this task delay, 1 second for this method call, and 1 second for this method call. Now, like we are seeing, these requests have nothing in common, so they are not dependent on one another. If, for instance, this one was dependent on this one, yeah, we needed to do this. But one thing we can do is, instead of awaiting, let's imagine this and call and we can do a bunch of things. For instance, we can do await result 1 and then await result 2. Now, how much time will this take? Refresh. And this time it took 2 seconds and a bit. Some of them was because it's the first request. Let's try again. Okay, now 2 seconds basically. So what's happening here is, because we are not awaiting each one immediately, the request goes through, the pretend request goes through, and we make the other one, and then we await. So both of them start basically at the same time. So this is called, then this is called, and then we wait. Another thing we could do, this is good enough because, yeah, it's good enough. Another thing we could do was await task dot when all, and pass them next result 1. And this will be, for this case, will be the same, because it will take 2 seconds, because they are parallel, and we'll wait. Now let's make a test. Into player and here we'll pass 1, 2. So how much time do we expect? So 2 seconds probably, because we are awaiting both of them. It's 1 second, 1 second one, we in 2 seconds the other. So make the request. So 3 seconds, like we expected. It's the worst case. So 1 second for this, and then 2 seconds for this, because this one it's quicker. We could do also when any, which is basically when one completes, it goes through. Let's check. Okay, so 2 seconds when this one completes. So this all is done. When this one completes, it's over. It ignores this one because we did when any. And that's about it. So this is interesting when we are doing external service requests that are not related to one another, so we can parallelize. But keep one thing important in mind. When we use entity framework, for instance, we, even if we are like querying 2 different tables, we cannot do this in parallel, because probably we are using the same database context, the same object, and that object is not thread safe, so we can't do this. We can only do this kind of things, these parallelized requests, when what we're using is thread safe. For instance, if we are making external API requests using, for instance, a HTTP client. HTTP client is, even if we use the same, is thread safe, so we can do it. If it's database calls, if we use 2 different database contexts, in case of entity framework, others will be different, but in case of entity framework, if we use different database contexts, no problem, they're independent. Okay, if we use the same database context, we can't do this because it might go wrong, because it's not thread safe. So that's an important thing to keep in mind. But it's useful to have this capability of doing parallel requests, because yeah, we can speed up some things. So if we need to call like 3 or 4 APIs, we just do them all at the same time, if they are unrelated, of course. So again, let me get back to the sheets. Oh, final topic, finally. So before going into the final topic, I was going to delete, but it can stay here. So the final topic is task completion source and cancellation token source. So this is interesting. For this, I'll create another controller. Call it no class new controller, demo queue controller, demo not recommended queue controller. Here, route queue. Index, we don't need no index. We need public action result. And ask is sync. Yes, we should use the cancellation token, but won't use it right now, or use it. No, not needed yet. So I'm going to create here a private read-only private static read only, concurrent dictionary, no, concurrent queue, and I will store here task completion source. This is a good idea. Task completion source of what? An integer. Let's call it queue, new queue. Is that enough? Is that enough? Probably. Let's see. So what I'll be doing is we get here and we do task completion sort of int, and then we go to the queue, we enqueue the task completion source, and then we result equals await tcs dot task, and then we return content result dot toString. So what I'm doing here is creating a task completion source, which is like the way we notify something that's happening. It's one of the ways we could transform non-async await APIs in async await. So we create a task completion source and put it in the queue, and then we wait the task for that task completion source. Now someone can go to this task completion source, not here, and set result or try set result. So let's see how. Let me just put here how ask. Now I go here, tell dot value, and do a public action result tell. This doesn't need to be async because we are not going to await anything. So if queue dot try the queue out var TCS, we can do something. If not, we can return, I don't know, whatever. So if we don't have an item in the queue, we can tell anyone anything. But if we do, we can go here and do if TCS dot, if not TCS, try set result. Well, int value. If not, we can no content. Okay. I don't want to put the same error code. Not found. It's not the best, but it's good enough. So if we have no no task completion source, we go not found. If we try set result and can't, we get a 500. This won't happen, but it could. Okay, so what we're doing here, we just remove this. Okay. So let's get back to here, and I'll open another tab. And if we see this is loading, if we go here, tell 1, and it's 1. If we ask again, we go here, 2, and we get 2. So I think you can understand what I did here. So we have a task completion source. We can await this, so we unblock the thread, and when someone makes this request, this await is completed and gets the result that we are passing here. Of course, this is not a good example, because if we take too long to call this, this will be blocked, like an open HTTP connection during too much time. But for other things, this can work well. Now let's make this even more interesting. If you didn't notice, this is a bit of a more advanced scenario, but I thought it would be interesting since we are talking about this, and it's not that hard to understand. So yeah, just before looking at another thing, the cancellation tokens, one important thing is that when you use this task cancellation completion source, when you set the result, this will run or try to run in the same thread that sets the result. So imagine this was on thread 1, this was on thread 2. Thread 1 went back to the thread pool. Now, when we do the try set result, this part of the code will be run by thread 2, because it's the one that's calling this. So many times it's no problem. Sometimes it could have problems. I haven't experienced them, but if we go here, for instance, David Fowler is really saying that. So this can unexpected code running on threads and can cause deadlocks and stuff like that. And there's an article also, The Danger of Task Completion Source, about this. I'll link this in the description of the episode. But the recommendation David Fowler makes is that we can do this. So when someone clicks sends the try set result, with this option it will try to run on a thread from the thread pool or what's available, instead of running immediately in the same thread. So tries to put it in another thread, and this code will continue. So basically what we had no problem, but it would basically set a result, complete this code, and then, from what I understand, then it will complete this one. So this would complete before this. With run continuation, this will set a result, ask a thread from the thread pool to handle this, and continue. And what was doing this continues doing this. This may have a small impact on performance, because if we do everything on the same thread, less context switch and all that stuff, it's better than all the context switch. But considering there's a possibility of deadlocks and stuff like that, this is probably a good compromise to avoid these problems in the future. Now, with this, let's take a look at cancellation token sources. So we've seen the cancellation token earlier. Now let's try to do something similar. So go here, instead of tell, call it cancel. No value needed. And over here we do try set cancelled. So we ask, we are blocked, we tell, we unblock, we ask again, we cancel, and we got an error because we cancelled it. All working as expected. Now another interesting thing might be, so let's make another queue like this one. We'll do a private static only. And cancellation token source. At least do it the same. Okay. And we'll do another one. Now we'll do a public async ask integer again. Did you know? Reaction result. And we'll call it wait async because why not? And over here we just better delay. We'll put here some value like value, and we'll do something like okay, I think this should be in a using cts equals new cancellation token source, and we can, for instance, wait task dot delay value cts dot token. What's wrong? Why are you complaining? Return statement. Oh, okay. Return no content. This basically just waits for something or a content. So if we go here, we delay, it will hold for 5 seconds and then waiting. Now we'll create another one here. call delay cancel. And we didn't do this here, but in queue we need to cancellation token source dot in queue CTS, and over here cancellation token source dot try the queue. This is the operator for I don't need it. It's the throwaway operator. So we enqueue the completion source, the cancellation token source, delay, and when it's done we just dequeue it. So because we don't need it anymore. But over here we can now do this as well. So if try the queue return not found, if not, if we did, we can cts dot cancel. So let's go here. We should get a not found because we have nothing there. But now let's delay. I'll add 10. It's waiting. Now cancel. Let's try again. It was correct, but this makes it more obvious. So waiting, cancel, delay cancelled, and an exception. So this is a way to, if it's basically what the framework does when in the controller we pass the cancellation token. Somewhere in the framework it cancels the cancellation token. That's what we are doing here. So we are awaiting this. There's a delay, we are waiting. We have the token. If we cancel, it's all cancelled. We could, this is as another constructor, which is basically I think this will work. So if we go here and hold, I think in 5 seconds it should go kaboom, and it went kaboom 5 seconds, because that's basically this is basically a timeout. But okay, yeah, let's take this. So this is a way to manually cancel a token. You use a cancellation token source. And there's much more things we can do with this. So let's wrap up. I think this video will be already too long. So wrapping up, there's a lot more to do with this async stuff. Lots more. Lots of things to be careful with. But like I said, in most cases, we do this. Async, await, await all the way. Use cancellation tokens so things can be cancelable. Beware of returning tasks directly. Don't do sync over async. And yeah, the recipe is this, but it's nice to have some more knowledge of what's going on. So again, feel free to ask some questions that I imagine will be. I will drop some links in the description, so you can check out some more things. Like Stephen Cleary has a lot of concurrency and async await content. I have here these recommendations for async and await in ASP.NET Core. Another article, David Fowler's tweet with people asking questions and stuff like that. Really interesting stuff. And I will eventually put these diagrams on a blog post. So yeah, I'll try to improve them a little bit before that. But yeah, that's about it. So hope you enjoyed it and learned something. If you have questions, let me know. If I said something stupid again, let me know as well. And I hope to see you in the next one. See yas!